All right, so let's talk about the particle swarm optimization. So, particle swarm optimization is a computational intelligence algorithm, uh, and the reason I like it is because it's pretty easy to visualize. It's easy to memorize how the algorithm works, and it's easy to implement too. It's not that hard. That said, particle swarm optimization, it doesn't solve all intelligence needs, right? It doesn't do everything for us, but it's kind of handy for solving some problems, and so that's why I like it. Um, so, what the heck does an optimization algorithm look like? What does it do? Let's make a little plot up here just to kind of consider. Let's say we've got x squared here. How about that guy right there? So we got x squared, so it looks like a parabola, right? Just like that. I'm pretty happy with the way that parabola turned out, to be entirely honest. Y equals x squared. And what an optimization function is looking to do is to find the minimum, right? Sometimes you might be wanting to find a maximum, but in this case, we're trying to find the minimum, or this point right here. All right, that's what we're trying to find. And of course, for some functions like y equals x squared, we can solve that analytically, right? We can just sit down and figure it out. So we use these simpler functions to kind of test out our particle swarm optimization, or any optimization function for that matter. But as it turns out, really when you're going to be using this, you're probably not going to have something that's easily mathematically defined or something that's kind of harder to solve. But here we're just going to use some simple functions just for visualization purposes. So let's look at something a little bit more complex, because particle swarm optimization, they can scale to multiple dimensions if we wanted to, right? So this is, I would kind of actually consider this to be a one-dimensional problem, right? Because we just have x as our input, and then y is something called our fitness, right? Y is our, here, I'll draw a little arrow, right? And so that makes this whole function, we call it a fitness function. And so the lower the value, we consider that to be the better fitness. A higher value is a worse fitness in this case. So let's think of this as a bigger function here. Let's think of it as really it's a three-dimensional function, but we've got two inputs. So we've got a y here and an x. And let's think of this as a three-dimensional, like a bowl. Like you're looking at it from the top. It's kind of like this weird square rectangular bowl thing. Right? And so it's kind of, these are kind of the contour lines. So if you imagine if we had a ball here and we dropped it, it would kind of roll around and eventually settle right here in the center, right? This is the point that we want to get to. This is our lowest value that we'd want to find. So the way our particle swarm optimization works is, let's first just imagine that these are like birds, right? They're kind of, right now they just kind of got willed into existence. They're kind of in some random spots. They got willed into existence and they're flying around, right? They're just kind of going in whatever direction they're going. Some of them are going fast, some of them are going slow, whatever. And what these, let's call them seagulls. By the way, seagulls are some of my favorite birds. I feel like they are vastly under-respected. Like, I don't know. I like seagulls. Anyway, the reason I like seagulls is because I feel like they're always at the places that I want to be. Like they're at a beach or like the parking lot of a shopping mall. Not that I want to be at the parking lot, but they're always kind of at the fun places, right? Where people want to be, right? Because there's food. Anyway, all that aside, the particles, or I guess in this case, right, the seagulls are looking for the best food source. And so let's say they just came into existence, and this is the best food source, and the higher up or the further away you get, the worse the food source is. But as they just came into existence, each one of these seagulls will initially say, "Ooh, this is a spot, right? There's some food here." But they've also got walkie-talkies, as all seagulls actually do, because they're all spies. And this seagull right here, he tells all the rest, he's like, "Hey, I've got a really good food source. In fact, I think it might be the best food source. So all the rest of the seagulls are going to take note of that. And that's going to influence the way they move or the way they fly. So there's three factors that are going to actually influence the way they fly. Their current velocity, the direction they're going, that's going to influence something. Their personal best is going to influence things. And the group best is going to influence things. So, for example, this particle is going to kind of go this way. It's going to kind of go this way. And it's going to kind of want to stay here because it thinks that this is the best. So, and of course, there's a little bit of randomness in there as well. So let's formalize this here with some kind of steps here. So the first thing that we do is initialize our particles. So we say initialize particles. That's the first thing we do. And so they're going to start off with a position P and a velocity V, right? And what's the next thing we do? The next thing we do is we find particle. I'm going to abbreviate that just as particle. Find particle fitness. So we find our particle fitness, and that's, in this case, this is be plugging it into our fitness function. So in this case, the fitness function would be mathematical. The fitness function doesn't have to necessarily be mathematical. This could be some sort of physical system that you might be running an experiment on. But here we just be plugging it in, and we get a value out. And initially, this is going to get assigned as our personal best. So we're just going to call that personal. Let's replace this P. Let's cross that out. We'll call it L, right? L is our location rather than P, and P will stand for our personal best. So L is location, P is personal best. All right. So each one finds its current fitness and saves that as personal best. How do we know it's its personal best? Well, it's because that's the only thing it's seen yet. Each one of these, as they start out, where they start out, they have to assume it's their personal best because they've got no other information. Obviously, that might change later. Then what's next? Then we need to find the group. Whoa, that was supposed to say group, not goop. Find group best, right? And so what do we want to call that? Well, we'll just kind of say, we'll store that in G. So each one of these particles knows its personal best, but then the whole group knows the group best, in which case it would decide that this is the best one. So that might be like a for loop where you just go through and look at all the personal best, and the best one out of that is the group's best. And now here's where the magic kind of happens, right? This is the heart of the algorithm. We're going to move the particles, right? We're going to allow them to move, and we're going to try a new spot. So the first thing I want to define is we've actually got this thing. I'm going to have a random number, right? There's some random numbers that we're going to generate, and it's uniform between 0 and 1. Right? So it could be 0, could be 0.79951, right? Anywhere in between 0 and 1. So we're going to move the particles, and as I said, this is kind of where the magic happens. It's going to be according to an equation. And the equation's got a couple parts. It's nothing too crazy. So we're going to have three components, I said here. We're going to have V new, right? That's our output. And so we're going to have three parts. We're going to have our velocity, right? We're going to take our current velocity into account. So current velocity. And what else are we going to take into account? We're going to take into account the group best, right? The group best and the personal best. Those three things are going to get taken into account. So, the way this velocity works is we're just going to have some sort of gain. So we'll just say k sub v. So this is something that we tune, or we kind of change around. So k sub v is just going to get multiplied by our current velocity, or v current. And then we're going to add that, and we're going to have our, this is our group best term, or how that affects our velocity. And so first we'll have a tunable constant, right? K sub, and so our group best is G. And that is going to get multiplied by a random number, right? So we'll just say R1. It's just a random number 1. We have a random number generated for this guy and a random number generated for this guy. They're not the same, right? We generate multiple random numbers is what I'm really trying to say. And what we do is we subtract our personal, or wait, this is our group best. So our group best location, from that we subtract our current location. So that's L, right? Our current location was L. So this is kind of giving us a vector pointing at the group best, and we're multiplying that. And then we've got kind of the same exact thing going on for the personal best, where we're going to have a gain multiplying the personal best. So that's P. We're going to have a new random number. And so here we're going to have our personal best minus our current location. And so that's what happens. Each one of these will move according to this equation. So let's just see kind of what might happen. Remember, there's a little bit of randomness in here on what could happen. The velocity has no randomness onto it, but the weight could be very small. It could be like 0.001, or it could be 1,000, right? It really depends on how you configure your system. So what we might notice is, even though they've got a velocity like this, maybe this particle might go like that. Maybe this particle might barely move, right? It might move to this spot, move to this spot. This one, it might kind of go like that, right? So it's going there. This one could shoot that way, and that guy maybe could go that way. So they're usually probably kind of want to have a big weight. Of course, this can vary a lot, but we might have a big weight on your group best. So everything's going to kind of veer that way. And then what happens is we want to reevaluate. So we want to reevaluate personal best. We want to reevaluate the personal best. So you want to say, hey, is this one, is it better or is it worse? So this one would probably be better. This one would be a little bit better. This one would definitely be better. This guy here, it started at this position and it went there. So this one might be worse. So it might say, hey, don't update my personal best because that last spot was better. But this one would also say it was better. So it's going to reevaluate personal best, and then what we want to do is reevaluate the group best. And so we always keep the lowest group best. So if we had uh, in this case, actually, if we said that this position was actually worse than this position, we would keep this guy stored as our group best, right? We always want to keep track of that very lowest value. Same with our personal best. We always want to keep track of our own personal best. And then what do we do? Well, we just loop back around to 4. And we just keep on looping and looping. And then we have some sort of condition. Maybe if the particles aren't moving anymore, or they're moving a very small amount, or if they've all converged, or if your fitness is within a certain range of 0. Maybe if we would set this in a loop to go until a fitness is at 0.0001 or something along those lines. So this is, in a nutshell, this is the particle swarm optimization, right? It's, oops, I'm a little nuts there. Particle swarm optimization is, it's very few steps to get it up and rolling. And I said right here that our fitness function here is defined mathematically, right? It's probably some function of x and y squared. But it doesn't necessarily need to be like this. It could be set up experimentally, or it could be based on like vision, or how close a recognized shape is actually to the real thing. Or for example, you could propose an experiment, say say we're in a room, and I've actually wrote a program and done this before. Say we're in a room, and you're starting here, and our goal is here, and let's say there's an obstacle like this, and you've got 2 dimensions. You've got steps forward and steps right. So you've got x is your steps forward, and x or y is your steps right. And so this could be, we don't know where the goal's at. We just know that we can measure how far away from it we are once we've walked. So what could happen is our particle swarm optimization, we could just say, we could give it a range, say, all right, it's probably no more than 20 steps in either direction, so don't generate anything bigger than that. And it could initially say, give us a few particles and say, all right, test this. Test going 5 steps forward and 20 steps right. And you would test that, and maybe you would crash into the goal. And so you would say, you know what, that's a really big fitness value. I'm gonna say, since I crashed, I'm gonna give you a value of 1,000. And then you look at the next particle, and that particle says, all right, go 2 and then 1. So you go 2 and then 1, and you say, all right, well, I didn't crash, but I'm still far away. I'm gonna give you a fitness value of, and you get your tape measure out and you measure it, and you say, I'm gonna give you a fitness value of 60. And then you get another one, and let's say it's 8 and 5. 8 and 5, and you test that out, and you're right here, and say you're only 5 feet away. And so that's what the fitness value for that particle would be, and maybe you do a couple more particles. And that would be something that you might be inputting into a system. And then after you've tested each particle's got its test results, you would run through this and calculate what the next test should be. And it's very likely that the next test will kind of be closer to your recent best. And things will kind of bounce around from there. So it doesn't necessarily have to be mathematical. It can be a physical system, which is very cool to start applying artificial intelligence, or technically this is computational intelligence too. So yeah, that's particle swarm optimization in a big nutshell, but it's very cool.